Yeah, really excited to be here to talk about Python performance. I hope you're ready. We're going to have a lot of questions, and this whole thing is going to be a quiz that we thought about with Adrien a few years ago, and we thought it would be really cool to do a kind of interactive talk. So you're going to have to use your smartphone. So if it's not ready, you can take it out already. And then we'll quiz you on multiple performance questions. But first, we can do a quick intro of ourselves, and then as well a bit of the quiz.
Yeah, so we are Arthur and Adrien. We are both software engineers for more than 8 years now. And 2.5 years ago, we founded CodeSpeed. So CodeSpeed is a dev tool that aims at optimizing and measuring performance of your code before the production, so directly in your CI, so that you can take action if you have regressions directly in your CI and not wait for your code to be pushed to production, deployed to production, and performance regression to affect your users. So really quickly, how it works. So you can just use your normal PyTest tests. You add a marker to mark them as benchmark. So a benchmark is a performance test.
So basically, this API is completely compatible with existing benchmarking tools with PyTest. But then in your CI, you will get a report. So here it's on GitHub, but it works as well in other places. And on top of this, we give a more detailed breakdown of the performance. And so this is basically exactly the same as we've seen on GitHub just before. But then where it really becomes interesting is that you can deep dive into every single test and have differential profiling. So here we're comparing two different profiles, and we're going to use this today in the quizzes. And as well, you have a breakdown of like how much memory is used, how much instructions are run, and basically the difference between a first run and another run. So that was it for the quick intro. It's already used. It's completely free for open source project, and we're really excited to support the ecosystem. And it's also used widely across multiple companies. We're really proud to help measuring performance.
And yeah, so why are we talking about performance? Performance of your code can be directly linked to multiple things. The first thing would be user experience. There are multiple studies on multiple companies that shows that every time you make your app faster, you have more retentions, more conversions. So it equals to more revenue, more money. For a lot of companies, I think you know about them, like they all market that they are blazingly fast, they are the fastest at doing things. So for a lot of companies, like performance is a feature and is a differentiator. Also cost savings, if you run the same workload faster, you will have less, your cloud bill will be smaller. And also, it's a good sustainability argument because at the same time, if you have less compute, then you use less energy. So that's why performance today matters.
And so for sustainability as well, improving performance of open source packages is even more important because you might have an open source package that runs on hundreds of thousands or even millions of servers, and improving its performance by 1% might lead to really dramatic saving and improve the footprint, carbon footprint.
But yeah, like performance is important, but performance is hard. Something happened. Performance is really hard. Humans are not machines. When we look at a piece of code, we can make assumptions. We can have an intuition about how it will perform, but from what we saw, building CodeSpeed and even in our own experience, even the best performance experts will be wrong, and it's a normal thing. We are not compilers, like we are not machines. We cannot execute the code, so it's really hard to get performance right. So that's why we had the idea of making this talk, and that's where we are going to see today. So if you don't trust that you can be 100% sure about the performance of the code, we'll see with the quiz.
So the quiz will be around a leaderboard, so where we will be counting points. Basically, the idea is simple. If you get a correct answer, you win. You earn some points. If you give the correct answer faster, you earn even more points. And the winner will receive a prize. So the prize will be a €50 gift card on Amazon or Steam. And the idea is that everything will be measured on CPython 3.13 on an x86 64 CPU. There will be no multi-threading, so it doesn't really matter which CPU it will be exactly. So you can join the quiz by scanning this QR code, or as well, there is a link here. So you have a link at the top. It's haha//
You have two QR codes, like.
They point to exactly the same thing. But yeah, the idea is that then you will have the interface so you can answer. And so every time it will go in 2 steps. First, we'll like show you the snippets of code that will benchmark. Then you will have the moment you need to answer. And then we'll give the answer and give basically the explanation of like why something is faster than something else, or something consumes less memory than something else. So we can start with the first question. Anyway, we still have a bit of time to join, and what's on the left will stay during the whole session. So here we'll compare 2 sleep implementations. One will sleep for 1 second, and the second one will sleep for 1,000 seconds using different libraries.
Yeah, and so there will be a countdown. Remember, you have to answer correctly and you have to answer fast. The first question, you'll have more time to answer, but the next one will be shorter.
So we can start it. And normally you have already the question.
So which is faster? Is the sleep 1 faster function or the sleep 1000 function?
There might be a little trick.
We'll talk about that.
And so time's up, and so every time we'll see the results.
All right, really interesting. It's a
it's
dead even. Never saw that. It's the third time we gave this talk, and it's always different. So yeah, pretty great. Okay, so unfortunately, it's not sleep 1 that is faster. Sleep 1000 is faster,
and
by a lot.
And the biggest reason is like the red arrow points towards it. It's not an async function, and we are not awaiting this async sleep. So it's just basically creating a promise and then returning, so not waiting for anything.
Okay, that was the only trick question.
It will get more interesting.
It will be more interesting. But as I show you, like the first question, we even got dead even. So yeah. All right, we'll continue with the first real example. So the first case study, what we want to do is counting even numbers in a list. So we have 3 implementations. They all have the same signatures. They take a list of integers and they return the number of even numbers. The first one, count4, is using a for loop on each element and it updates a counter. The second one is using the sum operator with a generator, with a generator list inside. And the last one is creating a list of the even numbers and then returning its length. As the input, we chose a list of 10,000 random integers. So yeah.
Okay. Now you have a bit less time.
Yeah. Now you have less time. So yeah, you have 10 seconds to answer. Which one is the fastest one between the for, the sum, and the len?
Okay. Okay, time's up. And so most of you answered with the sum one, but actually the fastest is the len one, and so here are the results. So it's pretty close. Really, the fastest one is really len, but between for and sum, it's really, really close. And we can deep dive into the why of like why is len faster than the others. First, if we take the sum one, actually every time we want to sum between like the content of this generator, there is some context switching between the sum function and basically this generator, because we have to go within the generator, get the next item, then come back, put it in the sum function. And even if sum is implemented in C and it's really optimized, the back and forth make it slower than actually len as we'll see in the next slide. The for one is as well a bit slower, mostly because of the control flow, which is bringing a lot of overhead, because basically we have this whole overall for loop that cannot really be optimized here, at least in this version of CPython. And so basically, it's slower than just doing a bare len on a comprehension list.
Yeah, I think it's okay.
Yes.
Well,
and now we have another question. So between all those three implementations, so basically we've seen that the fastest is the one using len, but which of those is using the least memory? And so this is this next question. Whoop. And so you have 10 seconds again.
So yeah, we were talking about execution speed. Now it's about memory. Which of those three is using the least memory?
Okay, and you get this one right.
Yeah, you got it mostly right. So yeah, and the results are actually quite interesting. So remember, count 4 was the slowest one, and count len was the fastest one. But count 4 is the one that uses the less memory, and by a huge margin, because count len is using like 4 million bytes of memory, and yeah, count 4 is using at least 100, not even 100.
Yeah, so because the count len is building the overall list, and then getting its length, which actually is really faster, but it turns out that it consumes way more memory. So here, basically, we are seeing a trade-off of performance, like execution speed against memory, and just speaking about performance can be a bit vague, and we need to always to clarify between execution speed or memory usage as well. And what we used to measure this is trace_malloc, so it's a built-in function that's actually pretty useful, and you can get something to measure memory usage pretty quickly. So here, for example, we just do a garbage collection at the beginning to make sure we won't measure some kind of outliers or things that actually we didn't want to measure really. Then we just say trace_malloc start, we run our function, then we get the output, and then we stop trace_malloc, and basically then we get the current memory usage and as well the peak memory usage. And so it's really useful because you can get really fast some insights on the performance of various Python functions. So
yeah, as we said, like one of the first learning that we have is execution speed sometimes comes at a cost. Here it's memory. We saw that even though count len was faster, it uses way more of the memory. So it's always something you have to take into account and not focus on just one metric and focus on more metrics. So here, execution speed and memory.
Oh, we can keep it then.
Yeah, so the next case study. Now, what we are wanting to do is to concatenate strings. So same thing, we have two functions. They have the same signature. We have a list of strings, and we want to return the string that is the concatenation of all the strings. The first implementation, concat plus, is using a for loop and storing all the strings, concatenating them into the result variable. And the other one is using the built-in join function to concatenate the strings. So the input is a list of size 5,000 with random strings from sizes from 1 to 16. Same thing, you'll have 10 seconds to answer which one is the fastest between concat plus and concat join.
Almost everyone answered. And yeah.
And now you got it mostly right. It was concat join. Nice. So
for this one, we're gonna do a live demo. We're gonna measure directly those functions. And so here I can switch. And basically here we are in P99, so that's a chat we created where basically you have a performance measurement feature, and you can give it snippets of code, and it will be able to measure and compare different performance and give you detailed profiling.
Yeah, and all the examples we've shown you, all the graphs, it comes from this tool. So now we just have a prompt, which is exactly what we just asked you. So we have the two functions.
So basically comparing the implementation, the performance, and then using basically some spec on the input, and as well some on plotting the detail.
So it's a live demo. It can go wrong, but it won't.
And so basically here it just re-implements exactly the algorithms, and then it will write some benchmarks, so using basically exactly what we showed you in the beginning, but with some parameterization to make sure that actually it's easy to compare the benchmarks. So it's using here PyTest parametrize. And here it's running, so in the cloud, and then we'll see the results. You can see in a few seconds. And so here we see exactly the results, and so yeah, actually we see clearly that join is way faster than actually the concatenation with the plus. And on top of this, here we can dive into the profiling data. And so basically here we see basically the new implementation, which is the one
it's concat join.
With join, and we actually compare it with the one with sum. And it's pretty interesting because we can have a look to the memory consumption here. And so basically we see the overall time, and we see basically the % of time that has been spent working with memory and basically reading or writing to memory. So here we can see in this one that it's actually pretty small, while in the new one, it's pretty large. But since overall this one is way faster, even if we take 50% of the time to access memory, it's relatively accessing less memory than actually the other. And so this is the explanation for this string concatenation with join being way faster than with plus, because every time we are basically using the plus equal operator, the string is copied into a larger string instance that's allocated to actually concatenate it with the small string we are concatenating, while when we're using join, everything is pre-allocated with the initial length of all the strings, and then it's only basically copying the characters without any.
Yeah. And as a side note, the memory allocation should be quadratic with this example. So, like if Python was not optimized already, this would have been way worse. So it's not the performance is not as worse as it could be. Because there are already some optimization with the plus equal signs. So yeah, but it's nothing compared to the. I was talking about. Yeah. So it's nothing compared to the concat join, because yeah, basically in the implementation of the join function, it looks at the size of your array and pre-allocates a string that is the right size, or almost the right size, so that you don't have to do reallocation every time. So it allocates memory once, and most of the time it's pretty good. So that's why it's way faster than the other one, which is doing a lot of memory allocations. So yeah, you have to think about string immutability, and when you concatenate a string, create new strings, you need to allocate more memory. And another good learning is that whenever it's possible, do not write code yourself, use built-in functions, because most of the time they are already optimized, and you don't need to reinvent the wheel. The third case study, now we want to compare list comprehension versus map operator. So as always, we have a list of integer, and we return a list of integer where each element is doubled. So the first one is using list comprehension, and the other one is not really Pythonic, but it's still using it uses the list operator and the map operator with a lambda function that applies to all the elements. We have a list of size 1 million with random hits from 0 to 999. Same as always, you'll have 10 seconds to answer which is faster between the list comprehension and the map.
Okay, time's up. Oh, nice. So most of you got it right. And yeah, the list comprehension is actually faster than using map, even if map is using only built-in functions almost. So here are the results. So again, we generated them with P99. We won't go through the demo this time, but basically using map, it's around like 15% slower. And we can see here the difference. And so to find out why it's actually slower, we're going to disassemble this code to have the Python bytecode, so basically low-level instructions, you can think about the bytecode as basically assembler, but run by the Python virtual machine. So instead of being assembler run by a CPU, it's the Python virtual machine that's actually running this bytecode. And so we'll disassemble the code, analyze the bytecode, and it will give us more insight on the performance and actually why it's slower or faster. So here is the disassembly. So it might seem quite a lot, but actually we can boil it down to the pretty simple sections that are highlighted here. So on the left, you have the disassembly of the list comprehension implementation. And the interesting part is the one that is highlighted in orange, where basically we are doing the for loop, and we are iterating, loading basically the data we want. So you can see here, for example, we are loading 2. Here we're loading x. We're multiplying it by 2. Then we're appending to a list. And basically this goes on and on. And on the right, we have the version using list and map. And so we can see that first it's loading the list function, then it's loading the map function. Both of them are basically built-in functions, so implemented in C, so they should be pretty fast. But then actually we see that most of the time it's calling the function that's here, basically our lambda function. And here we are paying the cost every time we are basically going from the lambda to the map object. We are paying the cost of context switching, because that means Python needs to make a call. So basically saving some register and the state of the interpreter, changing context, running the lambda function, and coming back. So again, with the JIT and maybe some future optimization, it won't be the case. But here, in this specific case, it makes it really, really slower. Even if the code, the bytecode, as you can see, is really shorter, it's really less efficient. So as I mentioned, basically to recap, the context switching is really creating a big overhead. Inlining is not yet possible. As well, functions tend to make the code easier to read, obviously, and to write as well for humans. So in the other cases, you might think whether or not you should add a function. Generally, like if you want to have readable and maintainable code, it will be easier to have a function. But sometimes it will really hurt performance if you are really optimizing small pieces of code.
But yeah, it might change a bit with the JIT.
Yeah.
Next case study, recursion versus stack-based algorithm. This time we have an algorithm that wants to calculate the factorial of an integer. The first one is, I think, something you all know. It's a recursive function. When we are at 0, we return 1. Otherwise, we compute the factorial with a recursion. And the other one is a stack-based approach where we create the stack and then we pop it and do the calculation there. We are using n equals 20, and which one is faster between those two?
Okay.
Nice. I thought it was going to be more on the factorial, but yeah, it's still like you still see that it's a bit hard to understand. But yeah, it's kind of the same as the one before. It's still a bit factorial is a bit faster. Stack factorial is a bit faster. Yeah, same as the one before. We have the bytecode, and here the difference is also the.
Yeah, maybe we can dive into the details. Here on the left, we have recursive factorial. And so we can see that actually the bytecode is really shorter than the other stack factorial, but pretty much similarly to the previous case. Actually here we have a lot of context switching, because every time we need to call this new function, we actually need to context switch to call the other one. So overall, we spend a lot of time just switching from one context to another. While in the other one, even if we have a lot of code, basically this code doesn't really switch the change of context, and everything is really almost linear, not really linear because it comes back and there is an iteration, but the context always stays the same. We never go to another function. And so even if the code apparently is larger, and as well when we wrote it, it was way longer, it's actually faster. And sometimes it's a pretty useful trick to change a recursive function into basically non-recursive function and avoid some probably issues you maybe had if you wrote a Fibonacci recursive function and put it a huge number within, and basically you reach the recursion depth the maximum recursion depth. This method also allow you to bypass these limitations.
So yeah, writing recursive functions might be easier to author and to maintain because like it's easier to think about, it's easier to read. But as Arthur said, there are a few issues with them. In Python, they will be, like in most of the languages, they will be slower to run. And we might hit the recursion limit of our programming language. I don't know if you already did the Advent of Code, but I know that for me it happened like at least once a year I hit that limit in Python. So I have to resort to change my algorithm to a stack-based recursion. And as we saw in the example, stack-based recursion algorithms are a bit more verbose, a bit more and harder to write. So yeah, it's a trade-off that we have to think about between maintainability and performance. All right, the next one is a big one. I don't know if you've been using Python these last 2 years, but we talk a lot about Rust and Rust with Python. For a lot of people, Rust, rewriting in Rust is like the solution to all the issues of performance. We are going to dive into this world. So we are going to start with a really simple example. We are going to use a Rust import and Pyo3 with the goal to have our Python code call some Rust code. So on the right, we have the Python code that define two functions. The first one, square pi, is the really simple function in Python that takes an integer and squares it. So it's pretty simple. The other one, square rs, is doing the same thing, but calling square rust. And square rust is imported from our Rust code, thanks to both Rust import and Pyo3. So this is example is all like you can run this almost as is. And in the Rust code, we can see that it's a Rust function that takes an integer and squares it. So basically, both are the same algorithm, but one is implemented in Python, the other one in Rust. And both are Python functions. And yeah, so the input that we are going to test with is 10,000. So we want to square 10,000. So which one is faster between square pi and square rs? Yeah, you got it right. So the idea is that with this really simple example, we can put away that Rust is not always faster than Python, depending on what you're doing. So yeah, for this really small example, of course, Python will be faster. Like multiplicating two integers is something that's already optimized in Python. We don't need to go to Rust to do that. So Python is still faster.
And we're also paying the cost, basically, of the overhead of calling the function and basically context switching. Yeah.
And also converting the type. So we have a Python type and int, and we convert it to a Rust type 932, and we are paying that cost. Also, it's an overhead that we didn't have with SquarePy because we are just using Python types. Okay.
Okay, so next, we talked about Fibonacci just before. And so we'll try it this time with Rust, comparing it with the Python implementation. So the Rust code might seem a bit different, but actually it's pretty simple, and it does pretty much the same thing as the Python one on the right. So basically, Fibonacci, we need to add each sequential terms and then return the overall sum. So basically, that's what we do here. We accumulate everything in B. So it's the shortest version we can do. And basically, we are doing exactly the same thing in Rust. So you can see the conditions are a bit different, and here the data type is a bit different as well. It's an unsigned integer of size 128.
Yeah, it's a bit bigger because I don't know if you know Fibonacci, but the result can get big pretty fast. So we need a large type.
And especially here, since basically we're running with n equal 150. So yeah, basically it's pretty much exactly the same as before, and so you have 10 seconds again. And yeah, if you didn't write some Rust code yet and integrated it within Python, really Rust import with Pyo3 is a really good like first start to get some Rust code within your Python code base. Oh, you got it right, nice. So yeah, 153 of you got it right. Rust is faster in this case, and by really a lot.
Yeah, so in Rust, what we are using is native CPU code for something as simple as Fibonacci. It's purely algorithmic, so it will be way faster than the CPython interpreter bytecode execution. So this is a good case of where we can leverage Rust with the native CPU code. So for algorithmic tasks, it will always, most of the time, it will be way faster than Python. The next example, so a bit more code, but it's pretty easy to understand. What we are going to do is a binary search. If you don't know, a binary search is we try to find the needle in a haystack. The haystack is a list of integers that is sorted in an ascending order, and we want to find one of those integers. On the right, if you look at the binary search py function, it's the basic implementation of the binary search algorithm. We start at the middle. If our integer is, if the value at the middle of the array is less than our needle, then we go to the right and we split the right list in two. If it's more, we go to the left. So yeah, we divide by 2 every time the search list. And it's exactly the same implementation that we did in Rust. We have a list of integers, and we do the exact thing where we split the array in 2. So yeah, the input is a list of 10,000 ints. So they are random ints, but they are sorted. Same question, which is faster between the two?
And last question, so you might decide who is going to win.
Yeah. Pretty interesting. But yeah, in this time, sorry to tell you that Python is faster and by a huge margin. Like, yeah, it's like 500 times faster. So what happened? What we did in the Rust function, I don't know if you saw, but the input type of the Rust function was a vec of U64, so it's a dynamic list of U64. So what we are essentially doing is that we are calling this Rust function, and when we are calling this Rust function, we are converting the type of the list to a vec U64. So basically, we are taking the whole list and taking it and converting it to Rust types. So we convert the whole list. So it's in O of n, but the algorithm, the binary search algorithm, is in log of n because we are splitting the list by 2 for each iteration. So as the input grows, we have n in front of log n, so of course that as the input grows, the Rust implementation becomes worse and worse. So there is a solution to that.
Fortunately.
Yeah, fortunately there is a solution to that. So instead, what we had before is that the Rust function was taking a list of U64. So it's the one on the left. Yes. Yeah. So the one on the left is the one that we had before, and the one on the right is the optimized version of the Rust function. So you can see that the sorted list type is a bit different, and this time we are taking the native Pyo3 types. So this is the Python version of the list. And instead of converting every element, what we are doing is that inside the loop, whenever we want to retrieve one value, we only convert that value. So that way, we'll only convert log n elements instead of the whole list.
And actually, we don't even really convert it. We access it directly in the memory. So we don't have to create a VEC that was created in the first one as well. So on top of converting, we had the overhead of just allocating memory, which was as well big O of n. So yeah, fortunately it's possible, but it just means that when implementing such algorithms and trying to use Rust, it's really important being taking a lot of attention on the types that we feed between Rust and Python, and the way we actually interop between the two, because you can get some really dramatic performance decrease and bottlenecks there.
And yeah, it's a bit hard to see, but now the Rust native types version becomes faster again than the Python version. So yeah, we talked about rewriting in Rust, and the learnings that we have from that is that for small functions, like we saw, like the square function and some others, like it doesn't make a lot of sense because Python is already well optimized. So it's not necessary to do those kind of things. We saw that for like algorithmic code with the Fibonacci example, Rust is going to be faster than the interpreted by code. But one thing that you have to keep in mind, it's not rewriting your whole code base in Rust won't be magically faster. You have to understand what you're doing. And for example, one of the biggest pitfalls is converting data from native types, and it also works the other way around. Here we showed you an example where we converted data from Python to Rust, but it works the other way around, when we come back to Python. So you have to be really careful about what you're converting from and to native code. And yeah, we wrote native code there because it's true for Rust, if you have Python calling Rust, but it's also true if you are doing interop with C++ or any low-level languages. So you have something that you have to be careful about.
So now a recap, more broad, on basically everything we covered. So it boils down to basically measuring, but human intuition can be wrong, and we saw it especially with Rust, where basically we're just thinking that rewriting, as Adrien mentioned, will be magically faster, but it's not always the case. And as well, depending on the use case and the data, we didn't really cover this, but depending on the data you put into an algorithm and the kind of benchmark you write around it, it might create some different results. So as well, creating different scenarios and measuring all those scenarios is really important to measure actually to get some direct consequences. And then as well, just measuring, because mostly we cannot just eyeball performance and guess everything that's happening, especially with as well changing version of CPython and new optimizations that are coming out for example, the JIT and many others that are actually having a real impact on just the simple code we can write. So now the leaderboard.
Oh, wow, super close. So yeah, congrats, Valentin.
Yes.
Yeah, round of applause. Yeah.
That was close.
Yeah, really too bad for Harry. Really too bad at 3 points. We never had something that close, so yeah, really too bad. But yeah, Valentin, come see us at the end, and we'll sort you out for the prize.
Yeah, congrats.
But yeah, congrats to everyone.
And then as a closing thought, so we showed you basically P99. And actually, this is completely free. We launched it, so the video quality is really bad here. But yeah, we launched it 1 month ago, and basically it's completely free. You can run some performance tests of various snippets, and so it's p99.chat, and you can basically, it will run performance testing. It works in Rust, Python, and we plan to add more languages. And so yeah, just try it out and give us feedback.
Yeah, and as all the examples we showed you, we run them with this. So yeah, it's pretty handy to compare really quickly this type of code. And the code is actually running in the cloud, not on your machine, so nothing to worry about bloating your machine, nothing like that. So yeah, thank you all for coming to talk.
It's now time for Q&A. If you have questions for the speakers, you are free to ask.
You mentioned about the recursive function, which is small logic has contained, does that mean we shouldn't use recursive function at all, or? Because I've noticed, like, okay, recursive function is just for readability and clean code, but not for performance. Is that right?
Yeah, definitely. Depending on the context and the size of the input, it will be worth it and safe to write a recursive function, and as well more readable, because sometimes you have as well really complex recursion where, for example, you're calling your function multiple times, and so basically just writing with the stack is possible, but it takes really more energy to think on how you'll do it. Maybe you'll have multiple stacks at once, and it will just be not readable. But usually, it's just faster to not write a recursive function if you can, but if the logic becomes basically too complicated, it's worth just using it so you get the benefit of readability, maintainability.
Yeah, and if we are talking about a few recursion steps, like if you're in your use case, your function can call itself only, let's say, at most like 50 times or 100 times, like the overhead is okay. It's more like when you have big inputs and like the recursion can become really big, where you can start to have issues. And as we said in Python, there isn't even a limit where you can have runtime errors because you hit the recursion limit, which you can completely override with a stack recursion based. Like you can go as far as your memory can go, basically. So yeah.
Yeah.
Basically, if you have, let's say like 10 to 15 recursive calls, I'd say like it's completely okay.
Thank you for that question. Another question? Okay.
Correct me if I'm wrong, and I'm really not sure. So I recall, as you were saying, that there is some like overhead to using lambda function to map function. It's the context switching that makes it slower. And here, I'm not wrong about I'm going to say, but you could use functions like partial and math.power, right? Or pow. So that would be much faster, wouldn't it? And is there some option to harness this to using some other function that you would yourself write in C or something, or Python? I don't know.
I think it might get faster, but even with like math.plus or anything, you might still have to pay the cost of calling this function, even if it's written in C. Maybe a cost that's smaller, but still having some cost. But yeah, definitely, as you mentioned, you could also use directly a REST function there instead of a lambda function, or any kind of function. Maybe it would be a bit smaller, but overall, using list map is not really recommended, and that's why most often we see list comprehensions, because basically it does pretty much the same thing and is a bit more optimized because you don't have to pay for this back and forth of the context switch. But if like you do a comprehension list and you put a function, then it will be exactly the same thing. So here it was a really specific example because we were multiplying x by 2. But if we would like call a function inside this comprehension list, it would be basically pretty much the same thing as using map. So depending on the context, if you're applying a simple operation on a list, it might not be worth it to, both might be pretty much similar.
Yeah. And anyway, it's a good use case for P99. You can just write the code and run the test, and like you actually see the comparison between the two. So it's actually a good thing to test.
Thank you.
Okay, one last question, please.
Yeah, I actually have two questions. So if you're super concerned about performance and you're performance bound, first why choose Python in the first place, right? Python is not the fastest language there. And second, you showed us comparison with Rust. Would you also compare it with NumPy or Pandas, which are also very optimized libraries that you can use in Python?
Yeah, actually, that's super interesting because exactly those libraries, in the beginning as well, we thought that Python was not really made for building really high performance applications, but most of the libraries we use are using compiled code. So if you think of PyTorch, NumPy, Pandas, really a lot of libraries are using actually compiled code and are really using something that's really efficient under the hood. And so using Python to wire things up is really just simpler than using pure Rust or some other language like C++ or something else, because just Python is like way simpler, and you can change the logic really easily, and it's really readable and understandable by most people. But yeah, definitely, otherwise, writing Rust is as well a good idea, but you might fight with the borrow checker in Rust, you might fight with the compiler in C++, or just allocation of memory and trying to optimize that. While in Python, basically, all of this is given, and you can do some optimization and get some pretty good performance out of the box. Yeah. And it will become even better by the time with the JIT, all the optimization we're getting.
And another argument for your first question is that most of the time you don't really choose what programming language you are using in your app, and it's not because you chose Python that you are doomed to have like not performance code. So even if you are doing Python, you will have performance consideration, and the idea is to show you that there are still possibilities either with rewriting in Rust or using more built-in functions and things like that. So even if you're using Python, it's not you are not doomed. You have some things to basically get yourself to something that can be really fast, and you have to measure it to know. But we don't have all the privilege of just changing to another language every time there is a new one that is faster. So yeah, that's it.
Thank you.
Thank you very much for that session. For the rest of you who have other questions, you feel free to approach the speakers. You can even post on the Discord if you have more questions. Thank you for the amazing session.
Thank you.
I hope to see you next time.
Thank you.